So we're going to look at what are called special triangles. So both of these special triangles are right angle triangles, and these two have very specific measurements of their angles. So we'll call this special triangle number 1 and special triangle number 2. In number 1, it's an isosceles triangle. Okay, so in other words, these two sides are the same, which means if this is 90, then these two angles must also be the same. Okay, so this must be 45 degrees also. And in our other triangle, we have a 90 degree, we have a 60 degree, and we have a 30 degree. Okay. What's special about them is we can find our measurements of our sides. They have very distinct ratios, the side measurements here. Okay. So for instance, we kind of refer to this one, the isosceles, of having legs or the side lengths of 1 and 1, and the hypotenuse is √2. Okay. And then for this one here, so in other words, the only numbers involved in this ratio are 1 and 2, right? And we just kind of have to work out where they are and where the roots are. And in number 2, there's a 1, a 2, and a 3. And we just have to figure out where they are. One of the values is √3, one of the lengths is 1, and one of the sides is 2. So the largest side is actually 2, because √3 is less than 2, which means the 2 is the hypotenuse. Okay. And then you have what you're left with are 1 and √3. Well, √3 is larger than 1. And if you're kind of forgetting which leg to put it on, just imagine this, that if this is 60 degrees, that means this has the wider opening, which means the side opposite would be longer than the side opposite of 30. Okay? So we put the longer side opposite of the 60 degree, and we just said that √3 was longer, which leaves us with a deduction of 1. So this is kind of a mental note, a way to kind of remember what side is equal to what. Now, these are just ratios. We can find, if you recall doing similar triangles in like grade 10, you can find triangles with the exact same angles with different side lengths, but they'll all be in relation to, there'll be a ratio of these side lengths, okay? And we're going to talk about those special similar triangles that do that. So, these are important. We also should be converting these to radians. So 45 as a radian, okay. I know that 90 is a radian. If I say 90 degrees is equal to pi over 2, well, 45 is half of that. So half of this would be equal to pi over 4. Okay. So we can always like memorize it in relation to something. If not, you can look up how to convert radians again. And which also means this is pi over 2. Okay. This one's also pi over 2. Now, here we go. 30 degrees is 1/3 of that, so essentially dividing 90 by 3. So if we divide this by 3, pi over 2 divided by 3, we just multiply 2 times 3 on the bottom. Yeah, pi over 6. And then here, 60 is double that, so that would be 2 pi over 6, pi over 3, reduces to pi over 3. So these, again, are just ways of, if you can only remember 2 of them, as long as you can think of relationships between them, you can kind of find the other radians when setting up. Eventually, you'll kind of just eventually memorize this information. Okay, so we should talk about the similar triangles and why they're important. When we have these triangles, we also have our basic trig ratios. We have our sine, we have our cos, and you have your tan. And these refer to triangles certain sides. So sine theta is equal to the opposite over the hypotenuse, cos theta is equal to the adjacent over the hypotenuse, and tan theta is equal to the opposite over the adjacent. Okay, this information is really important to us. If we are ever given sine pi over 6, so they give it to us as radians, we need to know what the opposite measurement is and the hypotenuse. Well, the opposite measurement is 2, 1, thank you. The hypotenuse is 2, so sine pi over 6 is the equivalent of 1 over 2. Okay, so we have to kind of keep that in mind. So we can essentially solve any of these relationships with these, whether it's sine of one of these angles, we can find out what the ratio is. The unit circle, and the reason they call it the unit circle, is imagine that there is a line kind of going around the circle, it's the radius, and it's 1 unit long. In other words, it's the distance of 1. Well, I can create a special, or I can create a triangle anywhere along this grid. Okay, so if the radius is here, and you tell me that this is pi over 4, measurement of pi over 4. I wish I zoomed in a little more for that. I need to know what the length, I need to know what sine of this would be like. let's say. So I can build a right angle triangle from this relationship, right? So if I draw a line straight down, okay, I draw a line straight down, I now have a right angle. Well, pi over 4, I know that's talking about an isosceles triangle, so this distance here, the distance of what would be considered your y, and this distance here, the distance of what would be considered your x, and the idea is here is imagine we have a coordinate at this point, right? And we need to know, let's say, x and y value. What are the x and y value of that coordinate? What would it be? Well, the x and y value of that coordinate, according to this information here, okay, so let's assume this is not the unit of 1 right now. Let's assume it's the hypotenuse of root 2. Okay, we know that in our special triangle this would be root 2, which would make this a distance of 1, and this a distance of 1. Now, this is where the special triangles come in. Because they call it the unit circle, remember I introduced it of having a hypotenuse or a radius of 1, we need to find a similar triangle to this one, okay, where this measurement, the hypotenuse, is just 1. Okay, so let's take that special triangle, and this is where the rationalizing comes in. Let's take that triangle, let's build the two of them again. So here's one of them, and here's the other one, which is a little bit smaller. Okay, we already know that this is root 2, this is 1, this is 1, 90 or pi over 2, and pi over 4. Okay, now the angles here are identical. Pi over 4, pi over 2, pi over 4. But what has happened is this hypotenuse has to be 1 unit. That's why, they call it a unit circle. This is essentially representing the radius in the unit circle. So if that's 1 unit, that means what are the measurements of these? Well, what did we do to this value here to get it down to this? Well, we essentially were dividing it, okay, by root 2. Root 2 divided root 2 gives you 1, which now means, well, what's 1 divided by root 2? Well, it's 1 over root 2. Yeah, exactly. Which means this is also 1 over root 2. So in terms of the unit circle, these would be the measurements or the coordinates of x and y.
Don't you make that root 2 over 2?
Yeah, so then you rationalize it. So if it's just a unit circle and they want to know in reference to a radius of 1, then this would be 1 over root 2 and 1 over root 2. But a lot of times we don't like this because this has a radical value on the bottom. So now we've got to go through the process of rationalizing this triangle, which is, again, it's fine. We're still finding another similar triangle. It's just a little different, this one. So this one's a bit bigger. Get in there? Yes, I can. We want this 1 over root 2 to be rationalized. So in other words, we got to multiply the bottom by root 2 and the top by root 2. So this triangle is going to be a little bigger, and you end up with root 2 over 2. This is root 2 over 2. And this value here would be root 2 times root 2. It's still root 2 over 2. It still ends up being a value of 1. Oh, sorry. Yes, that's correct. So sorry, I misspoke. This triangle is not bigger. It's just a fractional answer that's a little different. They've rationalized it, that's all. Not sure why I thought it was going to become bigger. So the hypotenuse is still 1. This is pi over 2, pi over 4. And all we did was rationalize our fractions. So we made them a value where the denominator wasn't a radical. Okay? The same idea can be built off of this triangle here. Okay? Let's refer it as to the unit circle. Okay? So let's get it. Let's draw it out again. There's one of them. Now this hypotenuse is 2, so the other one we're referring to is a little bit smaller. Okay. We knew that this was 2, root 3, and 1. This was pi over 2, pi over 6, and pi over 3. Okay. Angles are still the same, pi over 3, pi over 6, pi over 2. But this time, again, we need the hypotenuse to be 1 unit to be referred to in the unit circle. So in other words, what we're doing is we're dividing by a value of 2. So if we're dividing by 2, this then becomes 1 over 2. And this value here is root 3 over 2. Okay? And this one we don't have to rationalize because the denominators are whole numbers, so they're all set up. So if we look on the other page, this is kind of the unit circle going all the way around. As you can see, we have a degree. This is 30 degrees, which is pi over 6. Which can be written as root 3 over 2. The x value would be root 3 over 2, and the y value would be 1 over 2. Okay? And then, so that would be the special triangle. That's 1, 2, 3, we can call it. And this one, that's the isosceles triangle. You can see they've rationalized the answers root 2 over 2, root 2 over 2, and that's the exact coordinate we'd found. And then you can kind of build these as they go around the circle. Just realize that we're going from 0, 90. This becomes 180, which is essentially pi. 3 pi over 2, and then 2 pi is 360 degrees. Okay. So a lot of scattered information there, but that's kind of trying to address all the major ideas in special triangles.